Today I'm going to be talking about trajectories. And a trajectory is simply the path through the air of a ball, a football, a bullet, in this case, an arrow. And I chose this problem because even though it's a little bit tricky, it's a good lesson in how to break up a trajectory into x and y and use that to solve the problem. Okay, so I'm going to talk about problem number 29 from chapter 3 in the OpenStax College Physics textbook. So 29 states that an archer shoots an arrow at a 75-meter distant target, and that the bullseye is at the same height as the release of the arrow. So question A asks, at what angle must the arrow be released to hit the bullseye if its initial speed is 35.0 meters per second? So we know that the initial velocity is 35 meters per second. We know that the distance traveled is 75 meters, but we don't really know anything else about this trajectory. A good thing to keep in mind is that a trajectory like this is what's called a superposition of x and y. And that just means that you can break it down completely into an x component and a y component. And in order to answer the question, what angle must the archer shoot at, we're going to have to break up our vectors into x and y. Okay, so the initial velocity v0 is going to be at some angle theta taken from the horizontal. So in order to do that, we're going to think back to our trig and remember that a right triangle can be broken up into three sides with respect to theta. And the mnemonic device SOHCAHTOA should remind us that the sine of theta is just the opposite side divided by the hypotenuse. Cosine of theta is the adjacent side divided by the hypotenuse. And tangent of theta is the opposite side over the adjacent. So for the initial velocity, I can break it up into x and y by just multiplying the initial velocity by cosine of theta and sine of theta, respectively. And in x, we're going to talk about something called the range. And the range is just the distance that the arrow travels in the x direction. And the thing to keep in mind is that there's no acceleration, so there's a constant velocity. And that distance is just that velocity times time. So the range is just going to be the initial velocity times the time of flight. Or using theta, the range is the initial velocity times cosine of theta times t. In y, however, we know that the arrow is actually going to go up and down, and that's because of acceleration, and that's equal to negative g, where g is just 9.8 meters per second squared. The distance then is a little bit more complicated. We know that the final position is equal to the initial position plus the velocity times time, but then we do have this acceleration term at the end. But we do have a little bit more information, which is that the initial position and the final position are the same. Okay, so let's simplify things a little bit. So we know that y minus y0 is equal to 0. So now I just have velocity, I have g, and I have time. So let's get theta in there. Okay, so initial velocity times sine. Okay, so now I have this relationship, which I don't exactly know what to make of it, but it's going to come in handy if we relate it back to x. All right, so I have the x equation on the left, I have the y equation on the right, so I need to orient myself in order to solve this problem. So the first question I should always ask myself is, what are we solving for? And that's going to be theta. That was a question, right? So I'm going to label that blue. What do we know? Well, we know that the range is 75 meters. We know the velocity is 35 meters, and we know g. But then what don't we know but we don't want to solve for? And that's t. Okay, so that's red. So I'm going to rewrite these equations with blue and red. So I have these two equations, okay? So in order to get rid of t, I actually want to solve t in one equation and replace it in the other, okay? So I'm going to take the y equation, and in order to get rid of this t squared on one side and t on the other, all I have to do is assume that t is not equal to 0, because you can't divide something by 0, but if t was 0, then there would have been no trajectory, no time would pass, right? So I think it's safe to divide both sides by t. And then let's flip it around, because we're solving for t. And let's multiply by 2 over g to get rid of that. And now we just have that t is equal to 2 over g times the initial velocity times sine of theta. And now we're going to plug that back in to the other equation. Okay, so let's replace this t, and ooh, we got rid of it. Now we just have theta to solve for. It's kind of ugly right now, so let's group things together. Cosine theta, sine theta is not that easy to solve, but we have to remember something from trig, which is that sine squared of 2x is equal to 2 sine x cosine x. So I can actually replace that with sine squared of 2 theta. And now I actually have a relationship which you might be familiar with. It's from page 106 in your book, which relates the range to the initial velocity to the theta of the arrow. And you can just memorize this and use it in this exact kind of problem. All right, but we still have to solve for theta. We didn't do that yet. So let's isolate. Let's take the square root, and let's use an inverse trig function to pull out that theta. All right, so now I have this, and I can just plug and chug. All right, so let's just plug in all the numbers. I like to separate the numbers from the units, okay? So notice that the units are actually going to completely drop out, and you're just going to be left with a square root of 0.6, which is just this square root of 0.774. You take the arcsine of that, divided by 2, you get the answer of 0.443 radians, or 25.4 degrees. And so notice that I'm using 3 sig figs because the numbers they gave us were in 3 sig fig. Okay, so now we know about how to find the angle of the arrow as it leaves the bow. And that's going to help us solve a lot of other properties of this trajectory, and that's what I'll do in the next video.